Hello and welcome to the Abingdon Physics YouTube channel. Today we're going to be looking at Edexcel IGCSE Physics Topic 6, Magnetism and Electromagnetism, in particular the Electromagnetism section of that. So these are the spec points we will be covering today. There is a mixture of double award and triple award. Pay attention to when the spec point is in bold, because that will mean it is a triple award spec point, and when it is non-bolded, it means it is a double award and triple award spec point. So our first spec point is spec point 6.8, and it's to know that an electric current in a conductor produces a magnetic field around it. To show the direction of the magnetic field produced by this current carrying conductor, we need to use the right hand grip rule. So take your right hand and imagine you're revving a motorbike. So your fingers are all coiled and your thumb points in one direction. The direction your thumb points will be the direction of the current, and where our fingers curl to is the direction of the magnetic field. On a 2D drawing, this can be shown like so. An X indicates that the current is going into the page. So if I do my right hand grip rule with the current going into the page, we get clockwise circles for our magnetic field. And if we have a current coming out of the page, that will be shown by a dot on our wire. And so if we do our right hand grip rule again with our thumb pointing upwards, we will have anti-clockwise circles around that, indicating the direction of the magnetic field like so. So our next spec point is a triple award spec point, and it's described the construction of an electromagnet. So an electromagnet is where we wrap coils of wire around an iron core. And it's an iron core because we remember an iron is a soft magnetic material, so it means we can easily magnetize and demagnetize it. So this current travels around the iron core, creating a magnetic field, and the iron core also helps to boost the strength of that magnetic field. When we wrap the coil of wire like so, when it has a current through it, we get this magnetic field present. When we turn the current off, the magnet stops. So this is an electromagnet because the magnetism is only present when the current is flowing. So another triple award spec point is to draw the magnetic field patterns for a straight wire, a flat circular coil, and a solenoid when each is carrying a current. Well, the solenoid is an electromagnet, which we have just shown the magnetic field pattern for, and the straight wire we showed on the first slide. So let's look at the flat circular coil. So the flat circular coil is just like looking at a diagram where one wire is coming out of the page and one wire is coming into the page next to each other. This could be shown on a diagram like so. And what that creates is two circular field patterns in opposite directions, one clockwise, one anti-clockwise, and therefore we get a straight line emerging through the middle, like so. And this is the pattern that we would be expected to draw. So on to spec points 6.12 and 6.13, and these are once again double award spec points. And they are to understand why a force is exerted on a current carrying wire in a magnetic field, and how this effect is applied to simple DC electric motors and loudspeakers, and to use the left-hand rule to predict the direction of the resulting force when a wire carries a current perpendicular to a magnetic field. So first, let's discuss why there is a force acting on a current carrying wire in a magnetic field. So we've already discussed that when a wire has a current, it creates its own magnetic field. And it is the permanent magnetic field interacting with the current carrying wire's magnetic field that creates a force. So think whenever two fields interact, in this case two magnetic fields interacting, we will get a force. And we can use Fleming's left-hand rule to predict the direction of that force. So on your left hand, take your thumb, first finger and second finger, and each one of these represents a different quantity. The way I like to remember this is thumb thrust. They sound similar. Thumb thrust, so that's the force. First finger field, first field, sounds similar. And then, bit of fun, cursing finger current. So our middle finger, that second finger on our hand, is the finger representing the current. So cursing current, first field, thumb thrust. and they all sound similar. So let's set up a small question where we'll use this. So we have a wire with a current going into the page in between a permanent magnet, as can be seen by the north and south lines. So the first thing to do here is realize that the permanent magnet's magnetic field is going from left to right, i.e. from north to south. So let's draw those field lines on. So now we can do Fleming's left-hand rule. So first we have our current into the page, so we can point our middle finger into the page. Then we can see that the field is from north to south, so our first finger should go from left to right. And if we check, our thumb is pointing towards us, therefore the force will act downwards like so. And that's how we use Fleming's left-hand rule. So let's go on to the next example where we'll see it used in the motor question. So here we have the motor example. There is a current running through the coil of wire, creating a magnetic field. That magnetic field is interacting with the permanent magnetic field between the north and south wires, and then we are getting a force. So how can we work out which direction this wire is going to spin in? Well, let's take the side A to B first. We can use Fleming's left-hand rule again. The field, our first finger, is once again going from left to right, from north to south. However, our current this time is going away from us. This therefore means the force will be acting downwards on this A to B side. Whereas if we look at the other side of the coil, the current will be coming towards us, the magnetic field is still the same direction, so the force will be upwards. And that creates this rotation like we see in our diagram. We also have a split ring commutator, as we can see labelled here, and that means the current is flipped every half cycle, therefore meaning the coil will always spin in the same direction. Otherwise, the coil would get stuck because it would flip backwards and forwards, which would be unadvisable for a motor. And the other effect that we must know for both double award and triple award physics is the loudspeaker effect. So, a really critical part for the loudspeaker is that it only works with AC current. And that's because the AC current flows round the wire. Now, that flowing round the wire creates a alternating magnetic field. Because the current is also alternating, therefore the direction of the magnetic field is also changing. Now, the magnetic field that is changing is interacting with the permanent magnetic field of the bar magnet. And we remember from before, where we have these interacting magnetic fields, we get a force. But because the magnetic field from the wire is changing direction constantly, this force will therefore also be changing direction constantly. And this alternating force therefore causes the paper cone to vibrate backwards and forwards. And this vibration backwards and forwards of the paper cone creates areas of compression and rarefaction, and therefore a sound wave is produced. Both the loudspeaker and the motor are really common 4 to 6 markers, so it's really important we learn exactly how the process of both of them works. And they both come down to that idea of interactions between a permanent magnetic field and a magnetic field due to a current going through a coil of wire, therefore causing a force. So our last double award spec point is to describe how the force on a current carrying wire in a magnetic field changes with magnitude and direction of the field and current. Well, if we increase the magnitude of current, we get an increased magnitude of force. If we increase the strength of that magnetic field, maybe by moving the permanent magnets closer together, we also get an increase in force. If we change the direction of either the magnet or the direction of the current, we will get an opposite direction of the force. If we were to change both the direction of the permanent magnetic field and the direction of the current, the force would stay in the same direction. And you can check this out by doing Fleming's left-hand rule. So our last spec point for this topic is 6.11, to know that there is a force on a charged particle when it moves in a magnetic field, as long as its motion is not parallel to the field. Well, the easiest way to show what a question like that would look like is by drawing one out. So here is a box, and this box is indicating a magnetic field into the page. And let's imagine we have a proton in this field with a velocity to the right. Well, a proton with a velocity to the right is exactly the same as having a current through a wire going from the left to the right. So we can use Fleming's left-hand rule, but instead of having current as our middle finger, we've now got this proton's velocity as our middle finger. So our first finger, field, we can point into the page. Our cursing finger, current, we can produce to the right. Therefore, we should have a force going upwards. As the particle accelerates upwards, the force will continue to act at right angles to the velocity, and therefore we get this circular motion of the proton happening following this yellow path shown. So let's do some questions, and our first one will be on the motor effect. And so we have got this coil of wire with sections W to X, Y to Z. And our first question is to draw arrows on the diagram to show the direction of forces that act on the coil due to the magnet. So we need to use Fleming's left-hand rule. So our first finger, the field by the permanent magnet, will be from left to right, as that is where the north to south is. Our cursing finger, the current for section W to X, will be away from us. So it'll be up the page, and therefore the force will be straight downwards for that W to X section. And we can do the same thing for the Y to Z section. Our first finger field will be north to south. Our Y to Z, the current is towards us, therefore the force will be upwards. And we can see that that is what we expect because the motor should be rotating around that axis. So let's get on to part B, and it says explain the motion of the coil of the wire, refer to magnetic fields in your answer. So the question is specifically telling us to talk about the magnetic fields. Well, we know that there is a magnetic field generated by the current travelling through the wire. And that magnetic field interacts with the permanent magnetic field of the bar magnets between north and south. Therefore, these two fields interacting creates forces, and we can see that on our diagram, which we've drawn before. There'll be a downwards force from W to X and an upwards force from Y to Z. Therefore, these forces in opposite directions, on opposite sides, will cause the coil to rotate. And that's what we're expecting for our answer. And if we check our mark scheme, we see that we would have got all 7 marks for this section. So arrows drawn on W to X are up, Y to Z are down, and magnetic field around the wire, interaction between this field and the field from the magnet produces a force. Forces are on opposite sides and are in opposite directions. Coil starts to rotate. So our next double award question is about the loudspeaker, and it's asking us to explain how the loudspeaker produces a sound wave when there is an alternating current, an AC current in the coil. And it's really important it's an AC current, and we'll get into that in a second. So our answer is going to be there's an AC current in the coil of wire, and this produces a constantly changing magnetic field. The constantly changing magnetic field produced by the coil interacts with the permanent magnetic field due to the magnet. This interaction between the changing magnetic field and the permanent field of the magnet causes a constantly changing force which acts on the paper tube. This constantly changing force acting on the paper tube causes the paper tube to vibrate backwards and forwards. This vibration of the paper tube causes rarefactions and compressions of the air nearby, creating a sound wave. And if we check our mark scheme, we only needed 5 of these mark points, but I believe we should get all 7 because the current in the coil of wire produces a magnetic field. The direction of the magnetic field is constantly changing. The field of the coil interacts with the field of the magnet, producing a force on the coil. The direction of that force is constantly changing. Therefore, the cone vibrates and the air particles near to the cone are made to vibrate. So if you're double award, you can stop watching now as we're going to go to triple award questions from here. And our first triple award question is asking us to describe the construction of a simple electromagnet you may draw a diagram to support your answer. So our diagram should be an iron core wrapped with a coil of wire around it. And that is all we need to draw. An iron core with a coil of wire around it with a current flowing through it. There's no need to say any words here, so we can just move on to the next question, where the diagram shows a proton moving with a velocity v in a magnetic field produced by the SC. The direction of the magnetic field is into the page, using the left-hand rule to determine the direction of the force acting on the proton due to the magnetic field. Well, we get our left-hand rule out. We know that the first finger, field, is going into the page, and the current is the same direction as the velocity for this proton. And therefore, the force will be downwards. And as we can see, both our answers would have got full marks. The coil of wire with a current in the wire and an iron core, and the force would have been downwards. Now our final question shows a positively charged proton moving downwards in a uniform magnetic field. We have a force to the right and the proton's velocity going downwards. What is the direction of the magnetic field? Well, our force is to the right, so our thumb is going to point to the right, thumb thrust to the right, and our cursing finger current is going towards us. And that's because the velocity of the proton is the same as the current. Therefore, our magnetic field is into the page. Thank you for watching this video. This has been the Abingdon Physics YouTube channel, and this has been the electromagnetism topic. If you have any questions, feel free to leave them in the comments below. Thank you so much for watching. Please remember to like and subscribe. Have a good day. Bye.